Okay, it's gonna get pretty sciencey, okay? I'd encourage you to sit closer because I go fast. All right, so here we go. So today I'm gonna speak to you about the electrochemical assessment of coffee qualities. I wanted to include a QR code that is a link to the slides that I'm presenting because you're probably gonna need, you gotta chew on it a few times, all right? I'm gonna tell you about how I came to be in coffee first though. So I did my Ph.D. at the University of Bath in the UK. The city is founded in the year 3. I was there from 2011 till 2014, and I got into the coffee industry by helping write this book, Water for Coffee. Here's a picture of the spry version of me, Maxwell, Leslie, Ben, at Rimini's WBC 2014, where Max did the whole water spiel and augmented the flavor of coffee using the different minerals. After I did that, I spent 2 years in Boston. So I went from Old England to New England. Here you can see this is MIT, founded in the year, 1630. My office was right here. I could see the Charles River. It was very nice. It was nice to go back last year to the SCA, which was hosted there. And then, by chance, the SCA is now hosted here, which also happens to be where I now live, and I'm a professor of chemistry at the University of Oregon. Some of you have probably recently come to know the University of Oregon because of the film that's just come out, Air, which is a story of basically Nike's involvement in Michael Jordan's trajectory and his sort of building of the brand. Well, that is all based off of, we call him Uncle Phil, but that's Phil Knight. He's our biggest donor at the University of Oregon. But we're not only a sports school, so of course, we also have several US governors that have come through our program. The 6 NFL players, that's actually not true, it's more than that now. And Steve Prefontaine, who's I guess maybe one of the key figures that brought long distance running to the United States. Housed within this school is the Oregon Coffee Laboratory. This humble space is my lab, so this is where we get all the business done. You'll note that it's public. And the idea is because we make a ton of coffee, I would rather not pour it down the drain, so we give it away. And we invite anybody from anywhere in Eugene, or for that matter at the world, to come by. But Oregon puts some rules on it, so we are not allowed to provide cups and we can't handle food. And according to the state, food is milk and sugar, so we can only do black coffee, number one. And number two, we can't give away more than 100 milliliters. Otherwise, it's not a sample, it's a drink. And so as a result, my lab specializes in espresso. And we give away a ton of it. But actually what you don't see, I'll talk you through what is in the picture, right? We have a chest freezer that's filled with coffees that people charitably donate to us. We have a Simonelli espresso machine as well as a few other grinders, and a batch brewer that has also been donated to us by Bun. And we use this space to do all of the work that I'm about to show you. So it doesn't look like a fancy lab, but it's really about the people in it that do the hard work, and these are the group. So I have 2 halves to my group. One side is in materials chemistry, the other side is in coffee. The coffee folks are highlighted in red, and as you can see, Leif is not here. He hasn't officially joined the group, so he doesn't get the picture until he says yes. But basically, the group is then jointly funded, some on the National Science Foundation side, some from the Navy. Those 2 are not related to coffee, as you can probably imagine. And then we have research funding from the Coffee Science Foundation and a few other educational platforms. So I was thinking, how the heck am I going to start this talk today? So let's just get straight into it, shall we? Let's start with Nobel Prize 1907. This is Buchner. Buchner is widely regarded as the person who discovered enzymes. The experiment that he performed was grinding cells and showing that once you ground the cells, they were still able to perform fermentation. And so as a result, that was the discovery that there was something smaller than the cell, but still quite large, not the size of the molecule, and that's the enzyme. We now use this to ferment, for example, grape juice into wine. Now what's nice about this fermentation process is that you can monitor the change in gravimetric density, which is the white dots here, over time. So this is this axis here. And you can see that you start out with pretty dense water, that's sugary water, about 15% by mass, and you wait a while with the presence of enzymes, and you're going to turn it into ethanol. And as a result, you see a corresponding change in gravimetric density. And there was an observation made many, many years ago that the refractive index, which is the optical density, maps more or less to that of the gravimetric density. And we can understand that. You have 15% sugar turning into 15% ethanol, so the compositional difference between here and here is something that you should be able to monitor with a change in basically the path of light. But it turns out the real reason this works is that the refractive index is roughly proportional to the liquid density, which is related to the sort of microscopic interactions that happen between molecules and water. And so here you can see this is a sugary molecule interacting with water molecules surrounding it. And if you have different molecules solvated within, you have a different change in refractive index. And so here what I'm showing you is that you could have 4 weight percent ethanol for about 2 weight percent glucose, and they give the same refractive index. What this means then is if I shined a light at a liquid that contained sugar water versus alcohol water, they could in principle read identical, and you would not know whether it was alcoholic or sugary. That's not such a big deal because I like both of those things, but the real problem is that when we point a refractive index measurement at a complex liquid that is made of lots of different molecules, not governed by just one, for example, glucose in wine, we then run into a bit of a problem. So the industry has evolved around this brew control chart. As many of you will know, this basically relates the total concentration of coffee material floating around in solution. That's a gravimetric measurement, so that's mass of coffee floating around in mass of water. 2, the extraction yield, which I think of as an efficiency metric. So that's basically how much of the mass ends up solvated divided by how much you use to brew the coffee. Let's just do one quick example to make sure we're all on the same page. If I start with 20 grams of coffee, dry mass, and I extract 20% of that material, I will end up with 4 grams of coffee dry mass solvated. That's a 20% extraction yield, so that would be the x-axis. Now, if I add, let's say, I don't know, we've got 4 grams of coffee material and I add 400 milliliters of water, then we have now a 1% coffee material floating around in that liquid, and so that's the y-axis. And somewhere in the middle there, we've determined that coffee's going to taste good if we hit something like a 20% extraction yield and have it at concentration of, let's say, 1.2 to 1.4% or thereabouts. Okay, there's obviously some problems. We just heard from the previous seminar here that cold brew obviously accesses different chemistry to that of warm brew. And the easiest example of that is looking at color. Those colors come from the molecules dissolved within, but you can also do it from a sensory perspective. There's different composition within. Let me show you it in sort of a different data representation. And for this, we need to go back to the very first Nobel Prize in chemistry, Van't Hoff, who showed that the equilibrium constant, which is the extent to which a chemical reaction proceeds forward, depends on temperature. Now, why I'm highlighting this is it doesn't matter how long you leave coffee in a solution at 90 degrees, you're going to end up inevitably extracting something like 15 milligrams of caffeine per gram of coffee you use. And if I use cold water and I leave that to sit for a very long time, you're only going to be able to access something like 9 milligrams of caffeine per gram of coffee you use. And so as you can see then, as you increase temperature, you can access more caffeine. So you might think, oh, every molecule extracts more with higher temperature. But that's certainly not true. In fact, caffeic acid extracted the same, albeit there's not much of it, but extracts the same in all temperature regimes. Now, if you follow what Van't Hoff proposes, the idea is that if you increase temperature, you push a chemical reaction forward, that reaction required heat. So we call that reaction endothermic. Molecules that dissolve that release heat are called exothermic, and they actually will be pushed backwards. In other words, they will be suppressed at high temperature and will be extracted more at low temperature. And in chemistry, we typically teach people when they're diluting acids into solution to always add acid to water rather than water to acid, because the dissolution of acids in water is exothermic, it heats up. And so if you add a little bit of water to acid, you'll make steam and it'll explode in your face, whereas if you add acid to water, the water heat capacity will dissipate that heat. And so as a result, what I'm trying to say to you is that we can increase the extraction of caffeine at high temperature and decrease the extraction of acids at high temperature. So if I flip the temperature regime, I can flip the populations of these molecules. Okay. Then I look at Shahan's work, this very nice paper in 2016, where he actually studied the emergence of molecules as you're extracting in an espresso regime. This is, so we're all on the same page, water under pressure at high temperature, and the brew times are in the vicinity of, let's say, 0 seconds to 1 minute, okay, very short. Now, on the right-hand side, what you see is lightweight molecules, so carbon, hydrogen, and oxygen, and there's fewer of them than there are in this. So this is a lighter molecule, and what you see then is that under all pressure and temperature regimes, you quickly wet the coffee, and then you start extracting it, and the coffee is now being depleted of this soluble molecule. So this, over time, you're going to extract all of that stuff. On the other hand, the heavier molecule, you're still cranking it up as you're getting into the different pressure and temperature regimes. And you can see at high temperature, you get more of this one out than at low temperature, and so forth. Now, why I'm highlighting this bar in red is that at this 20-second shot, we're starting to get appreciable amounts of this molecule floating around in solution. But if I were to stop the shot at, let's say, 10 seconds, there'd be barely any of this molecule and still a ton of that one. And so we've been able to invert populations of organic compounds simply by now not only changing temperature, but by changing brew time. And so these are two different things. One is the rate in which we're getting it out, which is this picture here, or the kinetics. And the equilibrium constant, which is if I let it go for a very long time, what would end up being dissolved, that is thermodynamics. And so these are two competing processes. Now with that in mind, we wrote a paper on making fast espresso shots. This came out right before the pandemic. And in that paper, we did not have a good way of measuring what was dissolved in coffee, right? We simply were using the refractive index the same way that the rest of the industry does. And so as a result, we fit one diffusivity constant, which you can think of as the ability for the molecules to make their way out of the particle, and one rate constant for the extraction of coffee stuff. And this actually works pretty well because that's what the refractive index is measuring. It's sort of an average of coffee stuff making its way out of the particle. But it's a little problematic because, of course, when you look at small particles and big particles, they get wet at the same rate. And so, therefore, the little ones are starting to extract stuff from the internal portion of this particle before the big ones are even wet on the inside. And not to mention, if you go through the literature, you'll find that there is actually a diffusivity constant for one molecule, specifically in coffee, that has this value. So caffeine is at 2.4 times 10 to the minus 11 meters squared per second. And what I want you to glean from this is that this number is not the average, equal to the average of all of the molecules. Therefore, every molecule in coffee is being extracted, and at different rates, depends on different diffusivity constants, depends on temperature, time. You get it. It's complex. Not to mention also the size of the particles changes. We have a laser diffraction system that was hiding behind the glass window, and there's our lab out there, that gives us an idea of particle size distribution. Now perhaps if we have time, I'll come back to some of the spurious data that we've got there, but as a result, we were able to then generate a model that allowed us to predict the extraction yield as a function of the parameters that we would use in the production of espresso. And so this is what the model basically, you can think of it looking like. There's small pieces and big pieces. And as a result, one of the key outcomes was if you grind really coarse and use a little bit of less coffee, you're going to have a more even extraction. You're going to push extraction yield up, and it will get more reproducible. And that completely missed taste, obviously, right? So that's a problem. So I wanted to leave you at this point by saying that our model basically says that we can predict TDS and extraction yield, but we have a problem when we try and quantify what's dissolved within. So then we had to ask the question, well, can we develop something that allows us to, in real time, make measurements of what's in solution and hopefully then relate that to a sensory experience? Or at very minimum, perhaps we'll be able to make a measurement that is at least molecular specific, not relying on only refractive index to get concentration or strength. Okay, that was the warm-up. That wasn't the science part. So here's what my lab does. We use electrochemistry. Electrochemistry is defined as a chemical reaction that involves an electron, a negative, very lightweight particle, as one of the reactants or products. This is dissimilar to other types of reactions that you typically think of that involve nuclei moving around, the heavy pieces of atoms and molecules. And actually, there's a good precedent for doing this. So we can go through the endless numbers of Nobel Prizes in this topic. Arrhenius in 1903 showed that ions, so salt, breaks into sodium and chloride when you dissolve it in water. After that, let's take a time out for a second, actually. Okay, so sodium and chloride, it's not obvious that sodium is going to lose an electron to chloride and become sodium plus and chloride minus. In order for that to happen, an electron must be transferred from sodium to chloride. Therefore, that is an electrochemical reaction. So that's that first Nobel Prize, well, third Nobel Prize to Arrhenius. Nernst then showed, he basically advanced this, and you get the idea. And all the way up till 2019, there was awarded to these three for the development of lithium-ion batteries, which is indeed using lithium to generate electrons, which can then power things like your phone and your car and so forth. But to understand electrochemistry and to really put it all together, we need to go all the way back to the beginning of quantum mechanics. So bear with me on this. We're going on a journey. Let's start with the simplest atom in the universe, the hydrogen atom. Hydrogen has one proton, which is a heavy, positively charged particle in the nucleus. And surrounding it, somewhere in space, in its periphery, there is one electron. And as a result, the total charge of the hydrogen atom is 0. Okay? But this electron has to occupy some specific energy level. And so the basis of quantum mechanics is saying that it doesn't occupy all energy levels, nor does it occupy all space. It occupies well-defined positions in space at well-defined energy levels. And you can use a probability function to say there's a very good chance you're going to find that electron somewhere near this nucleus, because the positives like the negatives and other quantum mechanical stuff's going on. And it's going to be at some energy at some temperature. Okay? Now, I could shine a light on this material, and if I shine a light and that light's energy is equal to this gap, you can then promote the electron from the ground state to the first excited state. This energy gap is quantized, it's well defined, therefore part of quantum mechanics. Now the electron is here, and its position in space, or its probability function, has changed slightly. It looks something like this. What I'm trying to get to here is simply that the electron is now occupying a different energy level and is also occupying probably a different position in space. You're thinking, well, we got a long way to go to get to an espresso shot, and we sure do, okay? So let's go through an experiment where you can actually observe this directly. So you can point a spectrometer at the sun, and you'll find that not all colors of light are coming from the sun. There are well-defined missing colors in the sun spectrum. The solar spectrum, specifically, I'm going to focus on the F band and the C band, are actually attributed to this electron of hydrogen moving around, in this case from energy level 2 to 4, so from here to here, and for the C band from 2 to 3, here to here. Now, this gap from 2 to 3 is small. You don't need that high energy of light. That's red light. 2 to 4 is bigger. That's blue light. And so as a result, because the sun is made of hydrogen, you're not seeing those colors because it's just moving the electrons around in the sun. Okay? Nice. Let's do an example on Earth. How about this band right here, the D band? What the D band is the sodium in the sun. So you've probably seen sodium street lamps. The filaments are made of solid pieces of sodium, and when you heat it up, it emits the color of the sodium light. That is this yellow color. Well, the sun actually does have some sodium in it, and it's absorbing the sodium light, so you don't get the color of the sodium band from the solar spectrum. And so as a result, this is also why things appear funny color under a sodium lamp, because it's only emitting at this wavelength, and so you can't necessarily see all of the colors. Okay, so that's a manifestation of quantum mechanics that you maybe have interacted with in your day-to-day life. But what I really want you to glean from this is that electrons are negative particles, and they sit at specific energy levels that depend on the molecular atom. The two examples I just gave you were hydrogen and then separately sodium, and you can see that their bands show up at different colors. Okay, so now let's take a zoom in a little bit and consider a simple electrochemical reaction. This reaction basically is the addition of 2 protons to 2 electrons to form hydrogen gas. Now these 2 protons could come from an acidic solution. That's what an acidic solution is. It's a liquid that has lots of additional protons, H+ floating around. And you could provide the electrons, for example, from the wall. You could plug in and pump electricity into the solution, and those electrons from the wall would then find the protons in solution, and you could make hydrogen gas. And if you zoom in on what's happening at that metal-water interface, Basically, you have H plus from the water absorbing onto the surface of the electrode. You're going to have some H plus then sitting on this electrode surface, and then these little green dots are what I'm trying to show as electrons. They're going to come by, and if you have 2 electrons, 2 protons nearby, they may come together to make hydrogen gas. This is an extremely important reaction, right? Because if we want to move away from petrol fuel, you want to go to the hydrogen economy, you need to be able to make hydrogen gas efficiently. So this is something that is a very real thing that people are working on. But what I want you to remember then at this point is that to make hydrogen in this case, we added 2 electrons to the system. The addition of electrons is known as reduction. The loss of electrons is known as oxidation. So we're familiar with those words, right? But as it turns out, oxidation is a very specific chemical process where your molecule is losing electrons to its environment, sometimes to O2 gas, sometimes to other organic molecules, and so forth. Here's a mnemonic to help you remember this forever. An oil rig cat. This is a kitty that was found on an oil rig. On the left side, what you see is a molecule losing an electron. So that is oxidation is loss, oil, that occurs at the anode. On the other hand, reduction is gain, which is gaining an electron. That occurs at the cathode, and that gives you your mnemonic, an oil rig cat. I will continue to come back and remind you over and over again oxidation and reduction throughout the remainder of this. So, but I encourage you to try and internalize this for the future. Let's go for the example that is very real. All right, let's go for lithium-ion battery technologies. So here is a picture of a Tesla, and this car is powered by the so-called lithium-ion electrochemical process, where you start out with solid lithium. You're going to lose the electron to form lithium ions, and that electron is then going to whiz around a circuit and create electricity. Okay. It occurs at a well-defined voltage, so it occurs at 3.05 volts. So if you have a single cell lithium-ion battery, you're going to get something in the vicinity of that out of it. But on the microscopic level, here's how they actually work. On the left side, you have graphite, and inside the sheets of graphite, there are lithium zero. Okay? And on the right side, you have cobalt oxide. Now, when you connect a load so that the electrons are able to flow, what you will see is electrons will depart, the lithium will convert from lithium zero to lithium plus, and the lithium plus will move this way to then find itself intercalated within cobalt oxide. And if you allow this to discharge to completion, you arrive at a system where on the left-hand side you have graphite with no lithium in it, and on the right-hand side, you have lithium cobalt oxide, a new material. There's some problems with this. When you have lithium going between the sheets, you can imagine that there's a bit of a difference in size, physical size. So the battery materials swell, they fluctuate in size. And this was indeed one of the problems with the Galaxy telephones. You may remember they were spontaneously lighting on fire and you couldn't take them on the airplanes, was because the enclosure for the battery was not good enough to account for the sort of the swelling and fluctuation in size. But I think perhaps what's more interesting than the spontaneous formation of electricity is how you go back the other direction. Right? So in order to move the lithium ions backwards, you have to apply an equal but opposite amount of electricity that it generated. And so that means I'm going to have to add some sort of electrical source, let's say that applies 3 volts, to then push electrons back this way and incentivize the lithium to move back to intercalate between the sheets and therefore inevitably recharge the battery. So you get the idea. On one side, we have a spontaneous reaction where when we connect it, the electrons are flowing downhill. On the other side, we want to recharge. We're going to have to apply electricity and push the electrons back uphill. And so the difference between the high energy and the low energy is what we call the chemical potential, the electrochemical potential. You've seen this a million times. I'm giving you the high-tech version of it, okay? But this is a multimeter, okay? You connect a multimeter to either side of a battery, and it tells you how much voltage that battery can produce. That is a direct measurement of the electrochemical potential of that battery. And when it's discharged, that number goes to 0 because no longer will it have any ability to move electrons through a circuit. Nice. All right, I'm going to is there any questions, any burning questions before we really get into it? All right, let's do it then. So let's hit a nail, all right? So we have to have a way of referencing the electrochemical potential versus some well-defined reaction so that we know whether the electrons are above or below that reaction. If they're above, they're going to flow this way. If they're below, we're going to have to push them up the hill. And so we have this standard reduction table that basically says that reaction I mentioned earlier where you have 2 protons and 2 electrons, we're going to call that occurring at 0 volts, 0 potential. And if we have other chemical reactions, for example, we could take iron 2 plus 2 electrons to make solid iron. That's going to be more negative than that of hydrogen. What that means is, let's think about in real life. If you have a piece of iron, it's going to rust. So you have a piece of iron here, it's going to turn into iron 2 plus and then inevitably iron 3 plus. So it wants to go the opposite direction. If this reaction is written backwards, that number becomes positive. If that number is higher than that, then it's going to proceed spontaneously. So indeed, this is why iron rusts, right? Is that it is it's more favorable for iron to turn into rust than it is for it to sit there in nature. But how do we mitigate that? We can coat the iron in a material that is even more likely to rust, and that's zinc. So if you put a layer of zinc on the outside of an iron nail, zinc would preferentially form zinc oxide, which is the white material on a galvanized nail. And when it forms that, it protects the iron from the environment that rusted the zinc in the first place. And so this process is basically using a sacrificial material to protect the inside, the strong material. And so when I write this, when I flip them around, you can then see that this is more favorable. It creates more voltage than that of iron rusting, therefore will preferentially rust and protect the iron. Nice. You've seen this actually. Breaking Bad, season 1. They were cooking out in the desert, and the car battery failed, so they needed to generate voltage to get the solenoid to start the motor. In the show, they found galvanized nails. And the reason they did that was because they wanted that zinc 2 plus redox couple that I just mentioned. So the zinc to zinc 2 plus, because that gives us minus 0.76 volts versus hydrogen. And then they said that they also wanted the brake pads because they wanted the mercury from mercury brake pads. And the reason is because that gives you 0.85 volts versus hydrogen. This is a little bit of an embellishment. We don't put mercury in brake pads anymore for obvious reasons, because as you brake, you release the brake pad into the environment. So we moved on from this, but you give them the creative license. Here's what they were really trying to achieve. If you have zinc solid reacting with mercury, you can get zinc 2 plus and mercury solid, and that will generate 1.6 volts. And if you strap 6 of these together, you get 6 times 1.6 volts. That's sufficient to start your car. That's in the vicinity of a car battery. And so that was the basis of this. Here's an example of pushing an electrochemical reaction uphill. I can take a metal wheel and put it into a solution that has chromium 2 plus floating around in solution. And if I apply electricity to my wheel, I can take chromium 2 plus and turn it into chromium 0. Chromium 0, the shiny stuff. Does anyone know the technical name for this process? Yeah, electroplating or pimping of the ride. Yeah. So but it's electroplating because you're adding electrons to a metal to deposit yet another metal, therefore making a new shiny material on the outside of this sort of structural material, which is steel. People have been exploring this. It's a playground. Here's an example. One of the molecules responsible for the wet dog smell and cardboard in tainted wine is this one here. But you can make this go away, perhaps even taste like nectarine or lavender, by basically adding 2 electrons to this molecule in the presence of acid. And so, although it's not yet published, one could, in principle, stick electrodes into a corked bottle of wine and decork at least that molecule, making a fruit-forward flavor. You're loving it. Things are about to get wild, all right. So they also, as it turns out, have a flavor wheel similar to that of what we have in the coffee industry. Now, what is this device? Well, I showed you the multimeter, which measures potential. The opposite of a multimeter is one that applies potential, allows you to basically push electrons any direction you would like. And they range in price. So here at the SCA on tomorrow and on Saturday, we're going to have our expensive ones here. But you could, in principle, make one yourself from an Arduino. You could power it with your phone, for example. You could even just use your phone as a potentiostat. All you're really doing is applying voltage and measuring how many electrons are transferred, in other words, current, okay? And with that, when you apply a voltage, if nothing is transferred, then you won't see any current. But if electrons transfer, then you're going to see these peaks. And so with that in mind, these peaks then are well-defined voltages. And well-defined voltages depend on the molecule that's floating around, which means at specific voltages, I can hit specific chemical reactions of molecules dissolved within. I showed you one on the previous slide about cork-taining a wine. Let's zoom in and take a look at what's really happening at that electrode interface. So there's 3 panels here. I want you to actually sort of simultaneously look through all 3 of them. We put the electrodes in solution. In this case, a piece of platinum, carbon, gold, something that's not reactive, that's not going to oxidize. You know, picking iron would be a bad choice because as soon as you start applying it, it would just rust. Okay, so that's not a good option. And there's no applied voltage, so there's nothing happening yet on this one. We've got this piece of metal. It's got a well-defined energy level, the potential of the platinum. And then on the right-hand side, you can see a microscopic picture of that. This is me trying to depict platinum, a solution that has water molecules and perhaps some other familiar things like caffeine or chlorogenic acid. Now, if we start pushing positively on that piece of platinum, we're going to push, let's go back and forth here. We're going to follow that little black line right there, all right? We're going to go from high energy there. We're going to make it more positive. We're going to pull electrons away from that material, so it's going to drop down in energy a little bit. And at some point, it's going to drop sufficiently low that it will want to pull electrons away from molecules nearby it. And so you're going to start to see electrons flowing into your electrode, and therefore current is passing. So we're going to start to see a signal. And in this case, what we're doing is we're going to strip electrons away from chlorogenic acid. And at some point, we're going to make this catechol CGA derivative. Who knows? It might taste like something, but you get the idea. We've detected chlorogenic acid in solution. But that's not good because in principle, maybe we've changed the flavor of the liquid that we've just measured. So what you then do is sweep backwards. So we flip the voltage back around. We push the electrons back uphill a little bit. Once they're sufficiently high, they'll flow back into the chlorogenic acid if it's still nearby the electrode. And as a result, come back to the chlorogenic acid that as if we'd never touched it at all. Now you'll note this is cyclic, right? So we can loop around and we can detect things near the electrode. And so we call this cyclic voltammetry. But you'll also note that we did not see caffeine here because caffeine's electrons are lower in energy, so we would need to go even more positive. What that would look like is even going more positive, and then maybe we'd get some oxidized caffeine out there in solution, okay? Okay, so basically, we're just going to push electricity through electrodes dissolved in coffee. A lot of hard work to show you a picture where it's just sticks of metal and a shot of espresso, okay? The way this works is you need to have a conductive electrode like platinum that's going to do the work. We're going to monitor what's happening at that electrode. We have to have another electrode to close the circuit. So that's the counter electrode that just helps us make sure that we've got a complete circuit. And then there's yet another electrode called the reference electrode that we use just in case the conditions inside the liquid. Coffee's pretty weird in there, okay? So you need to have another electrode in there to tell you where you are relative to that hydrogen potential, relative to that zero line. Because you don't really know the voltages unless you have that reference. And we're basically going to push electrons through the coffee solution. So what are we pushing it through? A lot. Yeah, here, so this is a different picture. This one's a little easier to understand, right? There's a lot of molecules that give rise to flavor notes. It's hard to know whether the natural products on the outside have the same molecules giving rise to the flavor of blueberry as that of blueberry flavors in coffee, but you get the idea. There's a bunch of stuff. Now, we don't really know what we're measuring. We don't know what's floating around in a coffee. And in fact, we're going to use that to our advantage. I promise you, it's going to play out nicely. But what we do know is that families of molecules react at different voltages. Let me point out a couple for you, okay? So let's go for the aryl halides. So these are molecules like benzene with a chlorine bound to it. They show up at -1 volt. So if I don't go to that far, then I won't see them. Phenols, they're usually at +1 to +2 volts. Okay, nice. There's a few other things, amides, carboxylates, you get the idea. So they generally fall in these little categories. So basically, we don't really need to know what the molecule specifically is, but we can have a general feel for the sort of family of molecules it might be part of. A good family of molecules that you're probably familiar with are thiols. They typically smell pretty potent, pretty pungent. So that's another example of thiols are on here where you might be able to detect them specifically at different voltages. Now, we're not the first to think about this. In fact, a very nice paper was published in 2016 where a group basically used the same technique, an electrochemical technique, if you like, to detect the concentration of chlorogenic acid in coffee extracts. But I want to be specific. They did it not only in brown coffee, they also did it in green coffee extracts. So they can grind the green coffee up, they can grind the brown, they can brew it up, and they can measure through the electrochemical method the concentration of chlorogenic acid in solution. And they related that to the amount that they detected using high-performance liquid chromatography. And you can see here that those numbers, the ones on the left and right, are very, very similar to one another. There's a few other intuitive things to some of the roasters in this room. The green coffee has more chlorogenic acid than the brown coffee does. That makes sense because chlorogenic acid gets decomposed during roast to quinic acid and caffeic acid. Now you may remember early on in this talk I showed you that caffeic acid was one of those molecules that we were monitoring the concentration as a function of temperature. It's coming back here again. So I thought, well, why don't we just measure the concentration of chlorogenic acid floating around in solution, caffeine, caffeic acid, et cetera, and we can do that, right? So I can basically add in well-known amounts of chlorogenic acid, and our electrochemical measurement shows an increasing, basically a linear response. So if you take the area under here, that is linearly related to the amount of chlorogenic acid that we've got in solution. So I can construct a curve, I make the measurement, we know how much chlorogenic acid is in solution. Great. We can do it with caffeine. Great. We can do it with caffeic acid, and that's pretty neat if you think about it, because if I can measure chlorogenic acid and caffeic acid, now I know something about how you roasted the coffee. Because the relative populations of those two tell you a tremendous amount about how you got, and this sounds great. This is like, you feel like we've done it. And then I go ahead and put my electrodes in coffee. And what you see here, the first trace is the blue curve in this is brewed coffee. And we're looking, when I double the concentration of chlorogenic acid on the one on the left, you expect to see this bump just like grow in and say, oh, there it is, that's chlorogenic acid. And we see literally nothing. And when I put in caffeine into solution, I doubled the amount of caffeine. So this is a shot of espresso, we say it's got 100 mgs. I add another 100 milligrams of caffeine to this espresso. And I'm expecting to see caffeine grow in right here, just like we saw on the previous two slides, right? I'm expecting to see something like this. And what do we get? No difference. So that's bad. I had a bad day when the student showed me this. So we went back to the literature. And it turns out that caffeine and chlorogenic acid bind to each other. And when they do that, you can't see them electrochemically. And people have done these experiments. They have free caffeine. And what I want you to focus on is just the positions of these peaks. Free caffeine, free chlorogenic acid, these two little bumps. And when you put them together, these three peaks associated with caffeine shift. All of them do. And these two peaks shift the other direction, which means that they are forming an aggregate floating around in solution. This is really wild to me, because this means that the dynamic composition of coffee is binding up the different molecules within, so it's preventing our ability to directly measure caffeine without doing some funny business. Actually, I think this is a really cool result. It's pretty neat that the Coffee Science Foundation funds the work to study the flavors of coffee, and we're using that as the basis for an NIH proposal, because it may be true that caffeine is not as available to your body when it's in the presence of chlorogenic acid or all these other molecules that might bind it up. So that's awesome, right? So that we'll see where we go with this. This did not solve the problem, though. What I'm trying to get at is we do not have the solution to measure caffeine directly unless you dilute the coffee a tremendous amount. When you dilute the coffee a tremendous amount, the caffeine and chlorogenic acid separate and they float around in solution. This was so perplexing to us because I thought, oh, we're not seeing it because it's not concentrated enough. right? Usually that's what happens in chemistry. You're below the detection limit. In fact, quite the opposite. We dilute, 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 and we get to 0.01% TDS, and caffeine's like, boom, we're here. Crazy stuff. So what are we going to do? We had to move away from that approach. So if I take different electrodes, let's say we sample with platinum, for example, or glassy carbon, or another material, boron-doped diamond, you'll see different features growing in and out. What I'm showing you here in green is where we'd expect to see the chlorogenic acid. We would expect to see caffeine showing up in purple, and maybe it's hidden in there somewhere, but on the previous slides I just showed you, we can't resolve it. It's not available to us to monitor, at least at espresso concentrations. Now I want to remind you, though, that we have some lab rules. Lab rules are every shot we make, we need to be able to drink at the end of it, or at least give away and be confident we didn't kill someone, okay? So lab rule is, number one, is we got to drink it. Number two, we're not adding anything to it. So coffee is more or less a pH of 5, more or less, independent of how you brew it. For electrochem, people are happy with plus or minus 0.5 of a pH unit, so we're sort of in that range. And then finally, we can't add any electrolyte. And so remember that we're passing electricity through, but if it's really insulating in between, we're not going to pass electricity. It's just going to act like putting 2 electrodes on a piece of wood. You know, nothing's going to happen. Okay, so with that in mind, what we're going to then do is note that platinum does have some unusual features. These bumps over here, so maybe that's something associated with the coffee stuff floating around solution. And there was no literature on this whatsoever. So we're going to go ahead and target that. And I gave a seminar at the American Chemical Society meeting in Indianapolis about 3 weeks ago, and I still had no idea what these features were. And of course, all of you are wondering, is this a molecule in coffee that we could taste? And at the ACS, we got the answer. So these features are actually not related to coffee specifically, but rather water. Let me talk you through what's going on. There's a process called the hydrogen under potential deposition, or HUPD. When I put a piece of platinum in solution, we have water that is, in coffee, slightly acidic. There's protons, additional H pluses available. And if I start making that platinum negatively charged, the platinum is going to be negative. The protons are going to find that negative charge. They're going to first align like this, and then over time, you're going to see H plus get deposited on the surface of the electrode. And if you allow that to fully coat, you're going to get something like this. Now, we're at potentials or voltages that are insufficient to make hydrogen gas. Remember that reaction we talked about earlier? So if we keep going more negative, then we might actually make hydrogen gas like this. So why I'm calling it hydrogen under potential deposition is because we are not yet at the potential to make hydrogen gas, but we are depositing protons on the surface of the electrode. So what should dictate whether we can do that or not? Number one, of course, how acidic the solution is. If you have more protons available, they should deposit more. But number two, what if we were blocking the surface of platinum with other molecules, such as phenolics and other things that might stick to the electrode more favorably than that of the hydrogen that I just showed before? And indeed, yet again, we were not the first to think of this. I had to go back to a paper in 1973 that actually used this technique of depositing organic stuff on the surface of platinum as a method of cleaning water. Because indeed, if you stuck it in water, you would soak up all the impurities onto the surface, and you'd be left with clean water. And the result of that is these little bumps right here, these features are the hydrogen under potential deposition, so H readsorption or redeposition. And they were showing that as you have dirty water float over the electrode, you start to see a decrease in current passed because you're plugging up the surface with stuff that's not hydrogen. So what happens in coffee? Well, first experiment we did was let's just source coffees from notable roasters around the world. We picked Colombian coffees because I just wanted to see, could we tell a difference between coffees without even just naive, just push electricity through, do they have the same electrochemical response? And some of them were indiscernible, so the Transcend Colombian and the Necessary coffee, I couldn't tell the difference using some fancy statistics. The same is true with Passenger and Reveries coffee. But what we could see is that these were different to Tim Wendelboe's, and these were also different to one another, okay? And so that filled me with a little bit of confidence that we were going in the right direction. We just needed to refine our process. But why is this peak dependent on the coffee, right? Well, it turns out as you roast, you're generating more and more molecules that might stick to the surface of the electrode. So of course, then one might think that roast determines the feature that we're seeing here. But to ensure that it was hydrogen under potential deposition, the way you guarantee that is you do cycles. So you do a first cycle, and then without cleaning, you cycle again, and without cleaning, you cycle again. And if it is in fact blocking the surface, then current should get less and less and less as you go through more and more cycles. That's the smoking gun. And so that's what we see here on the left. We needn't talk about this today on the right. And so what we do then, I should just go back one slide. So what we do then is instead of just trying to integrate this bump, that's a bit problematic because it's really hard to imagine what that baseline looks like. We actually integrate all three of these bumps and we use the difference between cycle 1 and cycle 2, and then cycle 2 and cycle 3 to have some number which tells us the fouling rate. So the rate in which stuff is depositing onto our electrode. So with that in mind, I'm only going to show the first cycle for the remainder of the talk, but you have to appreciate that it's not just one cycle. We're actually doing sort of the delta between these curves. So what we can then do is we can then take a given coffee and we can dilute it, right? And then we do our 3 cycles. And what you'll see then is that the size of this feature depends on concentration. Okay, this is nice because, of course, the amount of stuff in solution should quickly deposit onto the electrode, and so you should see quick suppression of that feature. That's what we see, and it turns out it is linearly related. So total charge passed is linearly related to that of the TDS measured with the refractive index. But yet, we're not measuring a specific molecule at this point. We're still measuring all the molecules that are floating around in solution depositing on the surface. So it's not surprising it's linear, right? It should be linear with respect to TDS because it's an average still. So to do a better job than just sourcing coffees around from various different roasters, different farms, different processing methods, what we would then do, obviously, is roast some coffee ourselves in a systematic way to increase darkness or development time. So we have a small Ikawa roaster. And what we then did is we generated roast profiles that I think are relatively systematic by increasing the roast time by 30 seconds, and for every 30 seconds increasing the end temperature by 2 degrees Celsius. And so as a result, the products, you get something that looks aesthetically light and something that looks darker. I'm open to suggestions about how we can change our roast profiles to explore other things, of course, but this is what we've done, at least on a first pass. And I want to note then that the way we got to dark does really matter. So again, going back to some lovely work from Shahan, he has a nice paper in 2018 that shows that you can actually generate different amounts of volatiles depending on whether you roast fast or slow. In other words, how fast do you get to temperature? So in this case, he has two very nice plots here. So basically, if you roast fast and get to dark, you generate a ton of CO2. You roast slow and get to this fast and you roast to light, you generate that. And basically, light doesn't seem to change CO2 concentration independent of how you get there, but dark does. You get the idea. I'm going to leave the roasting up to you guys to think about whether my curves match onto your curves and how you can sort of relate my roast profiles to yours. That's not really the point, though. I just want to highlight that there's nuance in this roasting process. And so with that in mind, we can then take these coffees and we can brew them using the cupping protocol. We grind some coffee, we pour some water on it. At the end, we need to filter it, so we go through some paper. And as a result, we then get these cups, and they have the TDS of these are all over the place. So we then have to dilute to some concentration. So we picked, as best we could, 1%. And then we do the cyclic voltammetry. Again, we pass the electricity through. You get the idea. Now, what's really neat is that for these different roast profiles, we very readily see that as we roasted darker, this peak got smaller, okay? Now, that was also true in the subsequent scans as well. And what that's telling you, that as you roast darker, you're generating more of those molecules that are sticking to the surface. Therefore, dark coffee seems to have more of those things that are suppressing the hydrogen under potential deposition. And it allows us to have a linear relationship, yet again, with TDS versus the charge passed, or the amount of electrons that are moving around in solution. Now this is really neat, because now I can see the difference between a coffee at 1.2% that's dark versus light. Okay, so this has already taken a big step ahead of that of the refractive index measurement, because now we're seeing something that is compositional dependent on roast, which is intuitive for coffee professionals. But we can take it one step further and try and actually put a number on roast. This is somewhat of a futile exercise. If we have time, I can talk to you about some of the work that we've done on understanding charging and color and stuff in roast. But putting one number on a coffee that appears, let's say, dark, does not tell you how you got there. And Shahan's work, where he showed that you can change the volatile composition based on whether you go there fast or slow, really adds fuel to that fire. But let's just say if we did try and quantify the color, what you then get is another axis of color versus TDS versus charge passed. And for a given coffee, that creates a plane. And for this particular coffee, you can then basically take a quick electrochemical measurement, and that will tell you whether your roast has strayed off of this plane, or whether, for example, you brewed the coffee and you've achieved an extraction that is not falling in your expectation plane here. So this is a neat tool, because this is now allowing us to say, we have a quality control metric that depends on whatever is in the solution, some specific chemical composition. And so I don't really think of this as a brew control chart, because it depends on how you roasted it, what coffee it was, how you brewed it, all that stuff. It still depends on that. But you could call it an electrochemical brew control chart if you'd like, because it does the one thing that TDS can't do, which is provides you an additional handle that is coffee specific. But let's go back to the problem here. So hydrogen under potential deposition is kind of you're not measuring the coffee stuff. You're measuring the presence of the coffee stuff suppressing another reaction which is not coffee related. So that's a real conundrum for us, because even though it provides us the insight we're looking for, it's actually still not coffee specific, in the sense that a lot of things could give rise to the hydrogen under potential deposition curve moving around. So what we're trying to then do is make a measurement of chemical potential of this coffee, or any coffee for that matter, that is a measurement of molecules in solution. And so in order to do that, what you do is, instead of doing the cyclic voltammetry, you just put the electrodes in solution and turn the potentiostat into a multimeter. We're just gonna say, what is the voltage difference between these two electrodes? The same way I showed measuring the AA battery and saying it was 1.2 volts. And when you do that, this is a direct measure of what is floating around in solution. So here's what a typical curve looks like. It says that in solution, the potential in there is minus, let's say, 0.18 millivolt. Not a lot of electricity is available to be generated from this coffee. But interestingly, it's not zero, okay? So it is able to do something. Now, if you try and prepare coffee extremely systematically, what you could do is you could say massive coffee in, massive coffee out, shot time, TDS, all the things that you normally would do. I can then stick an electrode in there and say, how similar are they in chemical potential? I'm not a professional barista, so I didn't really try that hard. I mean, it was really hard for me, but I didn't try as hard as some of you probably could. But what we can see here is that this cluster here is 18 grams in, 45 grams out. It took about 29 seconds, but there was some spread in the shot time. There was some spread in the mass out. We have all the data, but my point is, if I just stick the electrodes in and measure the potential of those shots there, those all have a bit of spread between them. On the other hand, I could change something intuitive like the mass out and maybe grind setting. I was just messing around, but you get the idea. You can see these clusters. Now you might be looking at this going, Chris, well, they're not really that clustered. And also there's something weird happening here, right? Why is that sitting there? Well, it turns out that these ones were made with, these right here and these were made with one coffee, and then I ran out and I pulled out another coffee and it was a different coffee. So that's what happens when the boss goes in the lab, number one. But number two, this adds to my point. I can definitely see the difference, right? Because these all of a sudden clustered like this, totally different coffee. With that in mind, though, what we can basically do is take these data, and this is erroneously including these. This would even look even better if we got rid of these ones. And basically, you can fit a model which says, what was the open circuit potential, or the potential that we measured when we just put the electrodes in, versus an expectation value. And with that in mind, that allows us to have some confidence to predict whether the shots are the same or not and give you some sort of standard deviation. So let me tell you about the experiment that we're going to do. Well, hold on, I'm going to tell you. Here's a QR code. I need your help. So tomorrow, it's fuzzy because I didn't know how to make it high res, but please do sign up if you're available. So the experiment is this. We have a trained barista, a very skilled barista, someone who I trust that can do their very best to make reproducible espresso shots. And I'm going to let them dial it in. I'm going to let them use any tool they have besides electrochemistry to pick 12 shots that they think are the same. We're going to then blend them together to have like the mega shot, and we're going to dilute it, and that's what you're going to taste. Okay? Turns out doing sensory experiments on hot espresso is very challenging because it's cooling and you get the idea. So we're going to do it on cold Americano, but the key thing is the barista is going to select a lot of shots and we're going to blend them together, and that's going to be one sample. That's going to give us, we're going to measure that potential difference in there. That's going to give us their standard deviation, their spread of these curves here. We're going to then make that person brew a ton more shots, and I'm going to use the electrochemical method to select shots that are exactly the same, or as close to the same, better than they can do. And we're going to blend those together. And then you're going to use the sensory, the new descriptive analysis form. And you're going to show me that indeed the flavors of the one where I picked the shots that have the same composition are far more well-defined, less spread than that of the one that the barista did using all the tools that are available to them at the moment. Now, this is not proof, no matter what happens, it's not proof that we can measure what's dissolved in solution. But what it is an opportunity for is the development of a protocol which says if you select your shots using our method of basically doing this 1 second measurement and saying those two are the same, we can blend them. This will remove the spread in flavor profiles that you get inherently just by shot-to-shot variation because of the human, because of water flowing through the puck, all the stuff that has plagued my lab for years. So I need 15 minutes of your time, okay? We're going to make a whole bunch of shots of espresso. That part's the easy part. The electrochemical measurements that happen behind, that's the part that we're going to be spending a ton of time on. And you're just going to sit down and taste 6 coffees and log the data for us. There's 2 times. We have Friday from 2 until 4. And then Saturday, we're going to do 10 till 11. It was originally supposed to be 9 until 11, but I learned that we can't get into the convention center until 8. And then we can't prepare all this in 1 hour. It's a lot of work. But I want to leave you with, well, first of all, please come. Okay? We really do need the human data for this. The goal of this is for the machine to beat the human, okay? It's not a competition of you, it's me versus the barista. We're gonna win, okay? So, all right, so, look, let me leave you with a little bit of hype, all right? And then we got tons of time for questions and maybe some bonus slides. The first thing is we really struggled to understand the lack of ability to measure chlorogenic acid and caffeine in coffees that we knew contained both chlorogenic acid and caffeine. And we went the wrong direction and went for concentrated. But we now learned that going dilute will allow us to observe that. So that's the direction we're going now, is take a very, very small amount of a shot of espresso and dilute it in water and measure it that way. That's coming up. That's an easy one. But it's provided an opportunity for us to go seek NIH funding to support this work, to think about the availability of caffeine, a critical molecule that gets incorporated in all sorts of drugs far beyond that of coffee. So this is really a really interesting new direction that we're going. The next thing I showed you was that we have this very simple potentiometric measurement where I don't even pass electricity through the coffee. I just stick 2 electrodes in and measure its voltage in the coffee. And that's one way of sorting coffees that are the same or different, or maybe within a tolerance range or outside. This measurement is done literally in 1 second. This could be incorporated directly onto a machine. And instead of saying, oh, the shot channeled, it ran fast, you needn't worry about that. What if it ran fast but it actually has exactly the same composition? This would allow that to happen without the human having to make any decisions whatsoever. I can imagine it on a super automatic machine, but I can also imagine it in a very manual machine as well, right? You could incorporate it into the cup. Who knows? We showed that TDS does map more or less linearly, or at least on this plane, to 2 parameters that you're familiar with, roast color, as well as total charge passed electrochemically. And we think that that is a measurement of the hydrogen under potential deposition, which is an indirect measurement of what's dissolved in coffee. It's cool. I don't know if it'll be the thing that we end up using, but I think it's pretty nice because it gave us the insights we were looking for, at least on first pass. And then the thing that I'm pretty excited about is that we have a protocol now for preparing espresso-based coffee samples that allows us to ensure that those 2 espresso shots are the same prior to the sensory analysis. So that when you get to the sensory analysis, that allows you to make the assessment as to whether those shots, whether the variation is coming from the human or maybe some other thing, right, rather than the actual composition of the coffee itself. I'm pumped up about this because if the one contribution we have is teaching people how to do an experiment, there's no way I can do origin processing method, you name it. But there's a way that all of you could do it, and that's way better than me doing all that. Now, I want to leave you with a couple of exciting things. So we started out with Nails and Buchner, and somehow, using eChem, we ended up at the Ikawa and some flavors and measuring stuff that's dissolved in solution. And I gave one example of fixing the corked molecule in cork-tainted wine. Last night, I went out with Jeff Watts. We went drinking. And Jeff's into what I think is Brett or maybe lacto-tainted wine. And I like that, but maybe not every night. And one thing you can do is I can take the molecules associated with lacto-tainted and Brett-tainted wines and simply apply electrochemistry techniques, basically pushing or stripping electrons out of this molecule here. This molecule will then decompose into carbon dioxide, making bubbles. Oh, and the other molecule it makes is ethanol, which is great because then Jeff can have the wine that he wants, and I get a sparkling higher alcohol wine, which is great. Okay, we can do that. How about this one? This molecule on the left doesn't taste like anything. But upon the addition of two hydrogen molecules, or 4 protons and 4 electrons, this molecule splits into methyl whatever the heck that is. That tastes extremely strong of grape. Can you imagine the signature drink where I say add this molecule, taste it, put your cup down, the cup's made of electrodes, we pass the juice, and all of a sudden this thing is tasting like, boom, grape time, all right? It's coming. This molecule right here, 2-hexene-1-ol, can lose 2 protons and 2 electrons. In other words, this one can be oxidized to 2-hexanal. This does taste a bit like blueberry. This one tastes a lot like blueberry. So I don't only have to reduce the coffee, I can also oxidize the coffee and access even more intense flavors of blueberry. You get the idea. This is a playground. I'm only studying one very small opportunity of endless possibilities of flavor altering, fixing problematic flavors in beverages, and so forth. And so with that, I wanted to leave you with sort of the general overview here. If I had to give you one sentence overview, is that what my lab does is apply voltage or measure voltage in liquids. At least at this point, we've been able to transcend that of the TDS measurement from the optical system. And we can do it in real time. Now, as I mentioned, we had some coffee donors. That coffee really taught us a lot because it showed us that there's tremendous variation in the way that coffee is produced, not only in origin, but also in roasting. We've had many more than I could list here, but I wanted to highlight some of the earlier donors that have helped us in this research. Also, I know that I talked a lot about electrochemistry, and it's pretty hard, okay? This paper here does a nice job. It's open.